This session is to describe the another technique of knowledge representation in AI, that is the ontological engineering and categories and objects, mental events and mental objects. The previous topics of this module describes the technology for knowledge-based agent. The syntax, semantics, and proof theory of propositional and first-order logics, and the implementation of agents that use these logics. Now, in this session, we address the question of what content to put into no, such an agent's knowledge base, or we can say how to represent facts about the world. Before going to the main topic of the session, that is categories and objects, uh, I I would like to give a brief introduction of the ontological engineering. Ontological engineering, basically, it is a representation of general concepts such as events, time, physical objects, and beliefs that occurs in many different domains in the real world. Representing this abstract concepts is sometimes called as the ontological engineering. Through first order logic and predicate logic, we have represented the facts. Now let's talk about all the things related to the real world, that we can say events, the representation of events, the time in which that particular event happened, the physical objects related to that events, and the validity of those events like the beliefs. Okay, so let's look at into this particular tree. This is the representation, a general representation of the ontology of the world. And through this session, I'm going to describe the keywords written in this particular tree. And in this tree, each link indicates that the lower concept is a specialization of the upper one. So let's start with the uh, topic of the session, that is categories and object. First thing which I want to include is the organization of objects into categories is a vital part of knowledge representation. Although interaction with the world takes place at the level of individual object, so for that much reasoning takes place at the level of categories. What it means, uh, for the to interact with the real world objects, we have to perform much reasoning into the level of categories. For example, let's take an example. A shopper would normally have the goal of buying a basketball rather than a particular basketball such as BB9 or any other version. But a sports player will definitely focus on the version or the specification of the ball. So here let's take the example of shopper, not the sports person or the player. Okay. So a shopper would normally have the goal of buying a basketball rather than a particular basketball such as BB9. So categories also serves to make prediction about objects once they are classified. Okay, let's talk about the representation of categories in first order logic. So we have two choices for representing the categories that are predicates and objects. That is, we can use the predicate. For example, we have to represent basketball in a predicate form. So here we'll declare a variable b which represent the basketball. That means we can write basketball in bracket b, and it means b is a basketball as a predicate logic. But in terms of the objects, we can write we have to write just basketball. So these are the two representations of categories in FOL. Now, one more thing, categories serve to organize and simplify the knowledge base through inheritance. Okay, so keep it in mind. Another term which I want to introduce here, that is the subclass or subcategory. Subclass relations organize categories into a taxonomy, or we can say taxonomy hierarchy. For example, we can categorize basketball as a subcategory of balls. So we have to write in terms of the predicate, the subset as a predicate, and basketball comma balls. So here the meaning is basketball is a subset of balls. Let's take some more examples to represent knowledge, to represent the real world knowledge into the categories. So, the very first example is we have to represent an object as a member of a category. Means, example, we are to represent an object is a member of category. We are taking like basketball uh, basketball is a member of uh, or we can say BB9 is a member of basketballs. So we have to represent BB9 belongs to basketballs. If we have to write like basketball is a member of balls, so we can write basketball belongs to balls. Okay. Another example to represent a category is a subclass of another category. So here we are taking the example basketball is a subset of balls. Okay, so the representation is whatever written here in the second point, basketballs, the subset symbol, and balls. Now, for the third thing, all members of a category have some properties. To show this in the predicate, let's take X belongs to basketballs, implies X is a spherical one. That means we are dealing with some property of the ball X. That is, if it is a basketball, then it will be a spherical ball. Okay. Now, to describe another property, like members of a category can be organized by some properties. So here we can write it like we are dealing with some of the categories, some of the properties like the basketball, the color of the basketball is orange, and it is in this shape is round, and we are taking certain standard diameter, so on. So this is the predicate for that particular after considering those properties. Now the last one, to represent a category as a whole has some properties. So for example, we can say dog belongs to domestic species. Okay, so here we can represent a big category as a whole has some properties. Like property here we are representing as a domestic species. Like so we can consider certain animals as a domestic species, some animals as a wild animals. Okay. So the next topic is objects. Here we will discuss the things and stuff as well. The real world can be seen as consisting of primitive objects, like for example, atomic particles and composite objects built from them. Okay, so by reasoning at the level of large objects such as apples and cars, we can overcome the complexity involved in dealing with vast number of primitive objects individually. Here we have two more keywords, that are the stuff and things. Okay. So the category stuff as the most general substance category, specifying no intrinsic properties, and the category thing is the most general discrete object category, specifying no extrinsic properties. Now, what are the intrinsic and extrinsic properties here? So, for some properties are intrinsic, that means they belong to the very substance of the object rather than to the whole, to the object as a whole. Means, for example, uh, if we consider an object as an apple, Okay, we are considering an apple as an object. So here, a slice of an apple can be considered as the stuff. Rather considering the whole apple, we can consider stuff like slices of that particular apple. And extrinsic properties means weight, length, shape, and so on. Whatever is the physical property of that particular object will be considered as the extrinsic properties. Are not written and they are not written under the subdivision. Next point is a category of object that includes in its definition only intrinsic properties is then a substance or mass noun. A class that includes any extrinsic property in its definition is a count noun. Means extrinsic property basically deals with the numbers. Means number theory. Like for example, weight, length, shape. They deals with the numeric values. So those are the extrinsic property. Next topic is events. Here we will discuss two things, the situation calculus and event calculus. Whatever we had discussed in the previous sections comes under the situation calculus. And in situation calculus, the applicability is limited. What it means, it was designed to describe a world in which actions are discrete, instantaneous, and happen one at a time. For example, we have to fill a bathtub. Okay, so this comes under the if we are going with the situation calculus, so we can say two states of the tub. One when it was empty, and another when the tub was full. Okay, so we are not dealing with the in between states of the those two the initial state and the final state. So that is the situation calculus. But in case of the event, we deal with the event calculus. That means we have to the event calculus is basically based on the points of time rather than on the situation. Means what is the state at of that particular object at a particular time. So we'll deal with that thing. Okay. Next is event calculus refines fluents and events. Now, what is fluents? For example, let's take an example. A predicate at in brackets Shankar, comma Berkeley. So here we can the predicate me this predicate means Shankar is at Berkeley. So is an object this particular predicate is an object that refers to the fact of Shankar being in Berkeley, but does not by itself say anything about whether it is true or not. So the validity of this particular fluent is not shown here. Okay. Now to assert that a fluent is actually true at some point in time, we use the predicate T as. So we here we are going with the true and false value of that particular predicate. So we have introduced a predicate T over the above fluent. So now we are writing T that then above fluent comma small t. So here small t is representing the true value of that particular fluent at a particular time. Okay, let's continue. Events are described as instance of event categories. The event for let's say take an example event E1 of Shankar flying from San Francisco to Washington DC is described as okay. Here we are considering the categories and object representation of the knowledge. So we can say even belongs to flying and flyer and here let's divide that particular predicate. Even okay, one minute, there is some problem with the mic. Okay, so let's okay. Even is the event here which deals with the Shankar flying from Francisco to Washington DC. Okay, so even belongs to flying first thing, and here we can say even belongs to Shankar as a flyer, and the origin of that particular flight is Francisco. The origin of even is San Francisco, and a destination of even is Washington DC. So we have represented the whole event here like this particular representation. Okay. So generally, we can say events is basically on the based on the time rather than the just initial and final state. We focus on the time in bit, bit in between the initial and final states, the different substates in between the initial and final states. So, for example, if we are considering the time, there are some predicates which we can use while writing the events. So, very first is t f comma t. Here it is fluent f is true at time t. Same thing if I write happens e comma I, that means the event E is happening over the time interval I, and you can go through the rest of the examples. The next topic is processes. Here the processes, any process E that happens over an interval also happens over any sub interval. That means if we are dealing with the with an interval of time, then that particular process happens over the subintervals as well. Categories of events with this property are called process categories or liquid event categories. The description is given below. For example, the event E belongs to processes and E happens at T1 and T4 time, and T1 is less than T2 is less than T3 and T4 there is the relation that implies E happens at T2 and T3. If we'll resolve this, the left hand side of the predicate, we'll get the right hand side. The very last topic of this session is mental events and mental objects. This is again a representation of knowledge about the real world. Now, knowledge about one's own knowledge and reasoning process is useful for controlling the inference. Basically, the mental events deals with the agent that should know what are available in its knowledge base, or what are the knowledges the agent already have, and what are the knowledges the agent required, or what are the knowledge they don't have. Okay, what we need is a model of the mental objects that are in someone's head or something's knowledge base, and of the mental processes that manipulate those mental objects. What it means, for example, we have a certain knowledge about certain object. Okay, already we have that particular knowledge. Now if we want to predict something, so what are the process we can apply on the available knowledge? So that comes under this particular topic. Propositional attitudes that an agent can have towards mental objects are such as beliefs, knows, wants, intents, inform, etc. For example, let's take an example. Here we can say Louis knows that Superman can fly. So the predicate to represent this particular knowledge is knows, comma Louis, comma can fly in the bracket Superman. So we have to read it like from inside bracket to the outside, like Superman can fly. The first thing. Now Louis knows that Superman can fly. Another fact we have here is Superman is a Clark Kent, and the presentation of predicate in predicate is Clark Kent is a Superman. Now, through above two facts, we can deduce the knowledge uh, as the third statement, third predicate. Here, Clark is a Superman, and Louis knows Superman can fly. That implies if we'll deduce that particular left hand side statement, that means Louis knows Clark can fly. Okay, let's take another example. For example, I know like 2 plus 2 is equal to 4, and I mm, and uh, let's take the mathematical example here. 2 plus 2 is equal to 4. And for example, 5 is less than, sorry, 5 is greater than 2 plus 2. Or we can say 5 is greater than 4. Okay, so we have two facts. The first fact is 2 plus 2 is equal to 4. And then the second fact is 4 is less than 5. Okay, 4 is less than 5. So automatically we can deduce from this knowledge that 2 plus 2 is less than 5. Okay, we have two available facts. The first fact is 2 plus 2 is equal to 4. The second fact is 4 is less than 5. So we can deduce above two facts like this. 2 plus 2 is less than 5. Okay, so in the mental events and mental objects, we should know about the what we have, and we should also know about what we don't have, and we need to know about the processes to find uh, those things which are not in our knowledge base from the available facts. Okay, so this is all about the topic. Thank you.